you, Glenn, Reynders and myself will give you an overview of the main results of subtask 2 of this annex. And this subtask focused on the building behavior identification. The aim was to develop methods to describe and to predict the energy dynamics of buildings. And we all know that this information is very important to facilitate actually the energy transition. There are different applications that need models that are able to well predict future behavior of buildings in terms of temperatures, but also in terms of energy use. So what was the aim of this subtask? It was first to develop and use some different data analysis methods which are suited to describe this energy dynamics in buildings. And we then also used these models in applications. We will show you how these models can be used in fault detection and model predictive control. And the idea was that we wanted to know how good some models work, what kind of data that we actually need to make these models. What we also did was try to link to other tasks within the annex. So for instance, we also linked to the validation exercise that focused on the building energy simulation models, but more on that later in this workshop. So in this brief presentation, we will only focus on the main results. More results are available in the report that we developed, which you will be soon able to download from the website. We worked in different common exercises, going from the buildings that also were used in subtask 3, and also the twin houses were used, where we applied these different application techniques. Now I will gladly give the floor to Glenn, who will focus on fault detection, and then I will show the results on model predictive control. So Glenn, you can go to the fault detection exercises.
Thank you, Dirk. Yeah, as Dirk introduced, we've took this task by setting up quite some work. As staff already said, it were a lot of working meetings pre-Corona times, but even also during Corona times, we had quite some interesting Zoom and Skype meetings. And all this started with this very simple exercise, which was actually a sort of a recap we did from where we were at the start of Annex 71, or in other words, at the end of Annex 58. So to get all the participants on board, we started by redoing this very simple round-robin test box exercise and asked participants whether they were able to use their models to predict the indoor temperature profiles within this box. A very simple, very controlled experiment. And as we see on the next slide, there was quite some good results on this. So most of the participants were able to get very agreeable temperature predictions out of this test box data, and we could conclude out of that in terms of accuracy and prediction quality, most of the models that were tested were scoring rather high. However, of course, this was still a very, very controlled environment. We did the round-robin test box, an empty box, not really a real building, and that was exactly where we wanted to go to within the scope of this annex. So on the next slide, you see that we took it one step further, and the main challenge within this subtask was, okay, we saw that we had some methods, some modeling techniques that were able to predict indoor temperatures, that were able to predict dynamic behavior, on these very controlled setups, but can we redo this? Can we reproduce these results also when we look to real buildings and when we look to onboard monitoring? As Lisha already mentioned earlier in her presentations, one way of reducing both the cost but also improving the acceptance of these measurements being collected for these different applications is to be able to do this through onboard monitoring and non-intrusive tests. And that's what we tried to do within the scope of this subtask to see can we do this in real life. So the first common exercise, we asked participants to predict the hourly energy demand for space heating and or actually the indoor temperature within these two buildings. We started with the Gainsborough case, and within the scope of the annex, we didn't request them specifically to aim for the best, to not necessarily use all the data and all the most expensive modeling techniques, but try to explore as many methods as possible to sort of fill this matrix with, on the one axis, on the horizontal axis, what is the ambition level in your data acquisition technique, and on the right, on the vertical axis, what is the accuracy of the outcome that we get out of that. And as you'll see on the next slide, we got introduced in this common exercise with some particularities, and more interestingly, also with some new modeling techniques. So what we saw immediately when we went through these real-time or real-life cases is that new modeling techniques were also introduced. We switched from Annex 58, where a lot of effort was focused on the characterization side and also on the physical interpretation of the building properties. We moved to more a black box way of predicting the actual response of the building in terms of temperature or heating power. What we also saw introduced was that there were statistical methods being used to not only predict the average profile, but also use stochastic methods to also predict sort of the uncertainty. So the lessons learned out of this first common exercise were that, well, when trying to predict the heating power, we, for starters, found that, well, this was not really the natural output of the system, but rather an input. And due to the fact that the buildings were thermostatically controlled, this introduced a lot of issues in identifying suitable models, for example, by the introduction of the nonlinearities of the thermostatic control. Secondly, there was an issue with sub-monitoring, where we were used to have very, very detailed controlled experiment setups. We now were struggling with the fact that in actual buildings, you, for example, measure the total gas consumption, the total water consumption, but not necessarily the breakdown between domestic hot water and space heating. So methods had to be developed in order to get an assessment of these breakdowns between, for example, domestic hot water and space heating to feed to the modeling techniques. And then, as I said already, with the new methods, we got familiarized with more black box approaches, as we were focusing primarily on the prediction capabilities here, and also with stochastic methods that also predicted the uncertainty and not only the average value. On the next slide, we'll introduce you to the fact that, okay, at the end of that exercise, we had a lot of discussions with the participants on whether or not methods were useful and feasible. And we actually concluded by the fact that it's very hard to identify general methods for dynamic characterization, for building performance characterization, because well, the method or the model that you need is very much influenced by the actual application you will use it for, and especially the way you formulate the model should fit this application. So we focused on the two applications, fault detection and model predictive control, and I will guide you further to the fault detection and diagnosis part, where we introduced people to the twin houses. Well, people were actually already quite familiar with them due to the Annex 58 project, but nonetheless, some changes had been made to these twin houses, making them also a bit more representative for real life, with having 2 floors now, with the bedrooms and everything. Also, the ability to introduce mannequins and thermal loads there. And what we did is there was a rather large experimental setup being introduced in the twin houses. Matthias will definitely tell you more about that later. But we hijacked a bit of a measurement time and experimental time to introduce some faults into the twin houses. So we introduced 2 different faults into the systems of the twin houses, and the challenge to the participants was rather simple: tell us when and tell us what is happening in these houses. Now, because of a mismatch between the experimental time and our time here in the Annex, we started doing this on simulated data. So Irene made a very nice detailed model of the twin houses, in which we also introduced 2 of these errors. At least that's what we thought, that we introduced 2 errors. So we provided the participants with all the data that was also going to be available from the actual experiments. So indoor temperatures, operative temperatures, plug loads, outer weather conditions, etc. And we gave that for a duration of 2 months, starting in February, ending at the end of March. And the first month of that period, the building was actually simulated as if it were in normal operation. So everything behaving as supposed to, could be used as a training set, therefore. And then the second month, these faults were introduced. And well, on the next slide, you see what that data looks like. From looking at this graph, you can already see visually that something is happening in the very first periods, especially when looking at the heating power profiles, but also in the week around the 15th of March, something clearly is different in the behavior of the building. So when we zoom in on that, yeah, you can go to the next slide even, Dirk. We actually found that, or participants found that in the end, we didn't introduce 2, but actually 3 faults to the building. The first fault was that we introduced the fact that the underfloor heating system in the living room was continuously operating at maximum power. So sort of a valve malfunctioning between March the 2nd and March the 4th, 4:30 in the morning and 10:30 in the morning. And then the second fault that we thought we introduced was the fact that the ventilation system, the supply and the return on the ground floor level, was switched off between the 12th of March and the 22nd of March. But what actually had happened in the simulation was that we also accidentally introduced a third fault, being the ventilation system being switched off for the whole building between the 16th and the 22nd of March. And when we look at the results of the participants, we clearly saw some general findings out of that and some interesting findings out of that. First of all, in terms of the methods, Dirk, on the next we found that there was quite some interesting spread. So we were using some methods that were introduced already in Annex 58, but also things like ARIMA models and random forests were explored for their predicting capability with mixed success, as you can read in the report. A second thing is that only one team actually identified that something was going on with the heating power in the first week of the error period, and that mainly had to do with the fact that we fiddled with the heating system and that people were modeling the building as an input-output system, with heating power being an input to the system and the temperature being an output. And the fact that we changed something to the heating power meant that we didn't really introduce an error in the physical system that they were modeling. We were changing something to the input, and the temperature due to that varied according to what the model expected it would do. So these faults, input-output error faults, are very hard to detect with this type of setup. That was a very important finding. Secondly, we found, luckily, that almost all buildings or all techniques were able to identify these errors to the ventilation systems, which were actually, so the ventilation flow rate was mostly not used as an input to the model, and therefore there was an actual change in the physics of the system compared to the training period on which the models had been trained, and therefore these models were very much able to rather precisely predict these changes in the ventilation system. If you go to the next one, Dirk. So that's where we started to get confused. So we were only thinking about fault A and B up to this point, but when we first got the results back from the modelers, they clearly found that something else was going on, and they pointed us to the third error, which indicates that some way that there's also an extra value of doing these types of tests and these types of analysis during the design of a test case or during the design of an experiment, because this actually points out that these methods are that reliable that you can really use them to make sure that everything is working as supposed to during your experiments. Okay, then we go to the last slides on that. On the next one, Dirk, there was also something to mention about what the participants actually identified. So the previous discussion was on when do errors occur, and most of the models allow to identify that rather precisely, especially for the type 2 faults, not so much for the type 1 faults. But then when we asked participants to give an explanation of what is actually going wrong within the building, there we found that during these exercises, it was rather difficult to put a physical explanation for this, and only, for example, when relying on the gray box modeling and really look at the physical interpretability of your parameters, you could sort of identify in which parameters something was going on in your building, but really diagnose the physical cause of these errors proved to be very challenging. So all of that led us to work further on two specific aspects. A first one, which you will read more about in the report, is on linking the modeling technique and the detection technique to the type of error. So it was already clear from the discussion before that some errors, like for example the changes to the heating power, are difficult to detect when you're monitoring your heating power as an input to your model. So therefore, this framework was introduced where we had different types of faults and we linked different types of characterization techniques to them. A second thing was that when doing these first common exercises, we noted that the participants were often using manual and visual verification of their results to see when errors were actually being introduced and when they were occurring, and therefore some elaboration on the technical or the statistical tests that can be conducted during these fault detection processes has also been elaborated on, and we've now reported on a framework for these statistical tests where you can step by step see, okay, which type of faults can you detect with which type of statistical test. So that's in a nutshell what we learned from the fault detection part.
Okay, I had to go back to this slide because I could not unmute myself. Good, then we go to the model predictive control exercise. So we all know that model predictive controllers are quite useful in our chase to implement as much as possible renewable energy sources. And so we wanted to see to what extent the modeling approach and the model quality actually affected the results in such an NPC. And therefore we developed an NPC framework to demonstrate some of these opportunities. We also compared the NPC results against some well-tuned rule-based controllers to see what their benefits are. We used the twin houses again, and there the goal of the controller was to optimize the electricity consumption of the heat pump while maintaining a good indoor thermal comfort. So the key performance indicators that we used to assess the controller was the total discomfort, which was expressed in Kelvin hours. So how many times do we go above or below a certain temperature, and also the total cost of electricity that was used to heat the building. And therefore we used a given price signal. So in order to analyze all of this, we developed an NPC framework in Modelica. So the twin houses were modeled in Modelica as a kind of an emulator, and were controlled by an NPC. In order to make that NPC working, you need a model which can be trained on virtual data, but also on the real experimental data that we had from the twin houses. We provided two options to provide models in this framework. The first option was that the model was sent to us, and so we implemented the model in the emulator, in the NPC environment. A second option was that the developers developed their own optimizers and communicated through an API with the twin house emulator. So this optimizer was actually put out of the real model and communicated through that API. So we had several participants with several models going from gray box over state base and some black box models. I'm not going to go too much in detail, but you see that there's a nice spread of different models and also different options that were used to do this model predictive control exercise. You see some of the results, again, not too much in detail. More details can be found in the report. But you see the rule-based controller who actually does a good job in adhering to the set points. But if you look at the NPC, then you see that the model tries to also incorporate the price signal and use more energy when the price of the electricity is low, and also tries already to store some energy to better make use of the lower cost at that point. So then we also had a look at, okay, how can we now decide whether a model is actually good to be implemented in such an NPC. And at first we looked at the R² values of the different models. And then we made a plot in which you look at the electricity cost and the thermal discomfort. And we found out actually that if you look at the R² values and, for instance, the electricity cost, that there is not necessarily a good agreement. So models that are fitted on a one-step ahead prediction sometimes were very well identified, but that did not correspond into the lowest electricity cost. So we found that actually it is much better to look much better to the prediction capabilities by looking at multi-step ahead predictions. So there we found that there was much more overlap between the KPI and the actual KPI of the energy price and the discomfort level. So what we actually concluded from this model predictive control exercise was that the KPI does have to look into multiple step ahead prediction errors and not one step ahead prediction errors. That the NPC is able to outperform rule-based controllers, at least for this exercise. But in the next talk of Rule de Koning, you will see that this will also be the case for real-life buildings. And in this exercise, we were able to save about 24% compared against the rule-based controller. So it is possible to save costs while maintaining thermal comfort in the indoor spaces. So to conclude this results talk on subtask 2, some overall messages regarding the fault detection and diagnosis. We saw that different faults really need different detection methods, that statistical methods are able to help to automate the process of detection, and that the detailed building energy simulation models really were able to help us identifying these methods and finding some good research results. With respect to the model predictive control, we found that the choice of the model in the NPC indeed did matter. But even more importantly, that the key performance indicator that you use to identify which model is actually good is quite important. So there again, long-term indicators are much more suited than one step ahead prediction indicators. And if you do that correctly, it is able to use model predictive control to outperform traditional controllers. So finally, I'd like to thank all the contributors that helped us making this subtask 2 a very interesting one. And I would now gladly give the floor to Rule de Koning from DeltaQ, who will show an application of NPC in real life. Thank you for your attention.